How does Boolean algebra power digital electronics logic gates? Imagine a world where tiny switches turn on and off to make computers think and work. That's the magic behind digital electronics and how logic gates operate. At the heart of it all is Boolean algebra. Think of Boolean algebra as the language that tells these switches what to do. It deals with only two values, 0 and 1. 0 means off or false, and 1 means on or true. These two states match perfectly with the voltage levels in digital circuits. 0 volts usually means 0, and a higher voltage like 5 volts means 1. This simple system makes it easy for electronic devices to process information reliably. Logic gates are like electronic decision makers built from tiny components called transistors. Each gate performs a specific Boolean operation. The AND gate is one such gate. It only gives a 1 output if all its inputs are 1s. If even one input is 0, the output becomes 0. This matches the Boolean multiplication rule. The OR gate is another type. It outputs a 1 if at least one input is 1, just like adding true values together. The NOT gate, also called an inverter, flips the input. If the input is 1, the output becomes 0, and vice versa. These gates are the building blocks for all digital circuits. Transistors are the electronic switches that make logic gates work. They turn currents on or off based on input voltages. When a transistor switches on, it allows current to flow, representing a 1. When it switches off, it blocks current, representing a 0. Combining many transistors creates complex logic circuits that can perform calculations, store data, and make decisions. Boolean algebra helps engineers analyze and simplify these circuits. It allows them to write the circuit's behavior as a Boolean expression. By applying algebra rules, they can reduce complex expressions into simpler forms. This process helps minimize the number of gates needed, saving space, cost, and power. Boolean algebra also provides rules called laws, like De Morgan's laws. These laws help convert circuits into different forms. For example, an AND gate with inverted inputs can be replaced with an OR gate with inverted outputs. This flexibility makes designing circuits easier and more efficient. In real-world digital devices, Boolean algebra is used everywhere. It helps design arithmetic units, memory, data processors, and control systems inside microchips. Without it, creating reliable and fast digital systems would be nearly impossible. In short, Boolean algebra powers digital electronics by giving a clear mathematical way to describe, analyze, and simplify the logic behind electronic switches. It turns complex circuits into manageable equations, guiding engineers to build smarter, faster, and more efficient digital devices. This foundation is what makes modern electronics work seamlessly in our daily lives.